Okay, so very sorry not to be with you in person, but I guess this new technique is the next best thing. I'm going to talk about, how we can reduce CO2 emissions in the cement industry and how we can do this particularly using limestone calcined clay cement. Now, first of all, we need to appreciate just how important cement-based materials are in terms of all the materials we use. Materials based on cement make up nearly 3/4 of everything we use. That's not just in construction, that's everything. And then if you look at this graph, you look at the relative CO2 emissions, you see that, okay, yes, it's 8% CO2, but as proportion, that's a lot better than virtually any other material. So you're not going to help anything by replacing concrete by other materials. And sometimes people say, well, we've got to go back to using all bio-based materials, but that's just simply not possible in terms of land use. There was this report that was recently published by the World Resources Institute and another study that calculated that to replace just 1/4 of concrete with wood, you'd have to plant new forest 1.5 times the size of India. Now, maybe that would be a great thing to do, but even if we could do it tomorrow, that's not going to provide us with enough timber for another 30 years or so. So, despite the bad publicity for this project, I think we should ask, is concrete really the bad guy? Here we can see various different sectors and the equivalent CO2 emissions. So, cement and concrete is on a par with steel. It's actually less than clothing. Most people don't realize that. Passenger transport similar, and even food loss, food waste. So, again, we're not going to help it by replacing it. And we can achieve a lot more by lowering the CO2 impact of concrete than persisting in this delusion we can replace it by something else. Now, what's more, we actually have a lot of the solutions, and a lot of these solutions are relatively low cost. So this was a study done by the Mission Possible Partnership to say that, starting from the top, we can design better, we can have more efficient use of concrete in a building, we can industrialize the way we produce concrete to use less cement in concrete, then we can use less clinker in the cement. And these are all very effective levers to reduce CO2 emissions. It was even this study that these 3 levers here could reduce 76% of current emissions. So that's enormous. Now, after we've used these levers, we're not going to go to zero. We're still going to have a gap. There, people are talking about using things like carbon capture and storage, but there, the cost changes a lot. The cost would increase the price of cement by like 4 or 5 times. So the question is, we have these low-cost solutions, and why aren't we implementing them? Well, I've been thinking about this a lot, and one obstacle is that people want something perfect. We say the perfect is the enemy of the good. Yes, 80% is not the same as 100%, but if we can save 80% now, this is going to have much, much more impact on the climate than imagining, okay, in the next 30 years, we're going to have a zero solution. So let's do what we can now and start saving CO2 today, because everything we can save is going to be helpful for this whole climate crisis we're talking about. I think the second big obstacle is this thinking that there are these miracle green solutions. And, everybody plays along with this. Researchers play along with it because they think, I can get funding, I can publish this sexy paper in a high-impact journal. Venture capitalists think, I can make big money out of these new ideas, and big companies want to create the illusion that they're green when really they know that most of their sales are going to continue with traditional cement. So let's take a couple of examples here. You know, a great example is alkali activated materials. Billions of research dollars have been invested into this in the last 50 years, and there's pretty much nothing to show for it beyond a few demonstration projects. Now, why is this? It's not because there's some great problem to solve. It's because we're in this inevitable vicious circle. We have low volumes of consistent raw materials, which means we have a lack of robustness. You know, you can have a perfectly good formulation in the lab, but you take that to the field, you're going to have multiple failures. And all this results in high cost and inability to commercialize. So then people say, well, what about if we get calcium not from limestone? And this is possible. You know, basic geology comes down to this. You know, we have volcanoes. Volcanoes produce rocks, and on average, those rocks have the average composition of the earth. They're a mixture of mainly silicates, aluminates, iron, some calcium, magnesium, and the alkalis. Those 8 elements make up about 98% of the Earth's crust. And then the question is, well, you know, what happens over time? These rocks weather, and they break down the calcium components into this fairly pure limestone, and all the other components, you know, end up in the complexity of rocks we have. So you can go back to volcanic rocks like basalt. The composition is shown here. You can separate out the calcium. Basically, you dissolve it up in acid. These are common technologies in the mining industry. There's just 2 slight problems. First of all, the cost. Cost is about 20 times the cost of producing clinker today. But more serious is you've got about 80% of the material you can't use. So if you were producing cement by this technology, you would be taking from the earth 5 times more material than you actually use, and 4/5 of it would just end up in waste heaps. Same idea with calcium from seawater. I'm not going to go through all the details, but you can make a back of the envelope calculation and you come down to this ridiculously high cost. It's parallel to desalination, and you know, desalination is a well-advanced technology, but all the desalination plants we have in the world today would be the equivalent of about 5 to 10 clinker plants, in contrast to the 3,000 plants we have in practice. So I'm not going to go into any more examples. There's many presentations I've made on the web. You can contact me to know more. But believe me, all these so-called miracle solutions, they're totally impractical. They're too costly. They won't scale. Maybe they can produce some niche solution in 30 years' time, but we haven't got 30 years to wait. We have to do something now. And that takes us back to Portland-based cements, which we have to realize are an inevitable consequence of the chemistry and geology of the earth. The other thing we have to realize is that CO2 is a global problem. CO2 is a gas. It doesn't stay within the boundaries of the country that produces it. So CO2 being produced anywhere is the same all over the world. It's no good coming up with some nice cutesy solution like a lot of people in Switzerland. Switzerland's a very small country. Even if we stopped emitting any CO2 in Switzerland, it wouldn't make a big difference to the world's CO2 problem. And what we've seen in my lifetime is a very dramatic change in where cement is being used. So when I was born, a bit before 1960, the start of this graph here, almost all cement was used in what we called the global north. And in fact, in my lifetime, that's hardly changed. If anything, it's gone down. It's gone down and the population's increased. So in the global north, we're using a lot less cement than we were 60 years ago. But as you can see here, the big change has been the growth in China. which now accounts for more than half of all the cement produced. But now that's going to change again. China has developed very fast, used a lot of cement, and now demand is going down, and that requirement for cement is going to be taken over in the other developing parts of the world, most notably in Africa. That's translated into the demand for new floor area. The increasingly pale circles are the projected new floor area, and you can see this is going to happen most in Africa. Now again, what I want to stress is we can do a lot about this if we act through the value chain. First of all, we make clinker efficiently, we reduce clinker in the cement, reduce cement in the concrete, reduce the concrete in the building. And the easiest way to do this is this technology of what we call supplementary cementitious materials, where we replace clinker by other, often byproducts from other industries. And these are limestone, like we may have in the quarry. It's like slag from producing steel through blast furnaces. It's like fly ash from burning coal. But even today, the amounts of these materials like slag and fly ash are in relatively small quantities compared to the amount of cement we produce. And to confront climate change, the first thing we've got to do is stop burning coal. That means no more fly ash. Blast furnaces are a very inefficient way of producing steel, so the amount of slag is going to go down. And even today, we only have about 10% of slag compared to the amount of cement. So we have to really come to new materials, and this is where we have to look what's available. We have a lot of limestone, but beyond a certain point, this just becomes a dilution. What we have that's really underexploited are these clays, which can be calcined, that means heated up, to produce a very active substitute material. So this is the basic idea of LC3, limestone calcined clay cement. It is just another blended cement, but because the calcined clay is very reactive, we can go to very high levels of substitution, and we can maximize the incorporation of limestone, which is super abundant. So an example of an LC3, it's a whole spectrum of cements, but LC350, which means 50% clinker, has comparable strength to OPC. It has 40% less CO2 emissions, and some properties like chloride resistance and resistance to alkali silica reaction are dramatically improved. And we know the reasons for this. We have to have some of this mineral kaolinite. When we heat it up in the range 700 to 850, it becomes destructured, and then both the silica and alumina can react, this alumina notably with the limestone, to form these new hydrates which fill space and give strength and durability. The kind of clays we need are very widely available throughout the world. We don't need high-grade clays. In fact, they're even not desirable because they can create problems of workability. So all these orange regions are where we have abundant clays. And these are also coincident with the regions where population is increasing and we need the material. So as I said, we're not talking about high-grade clays, we're talking about any mineral deposit with 40% kaolin, even down to 30% is fine, and these can be things like dredging, sediments, aggregate washings, etc. Here are some examples: Belgium, Spain, Portugal, where they're reusing these materials. They're not clays like you use in pottery, they're reusing them for being calcined and incorporation in concrete. And we came up with this idea in the lab, but now it's on a full-scale industrial level. This was the pioneering plant from Colombia. This plant has been producing all its cement containing calcined clay for the last 5 or 6 years, and they're using it in all applications, like this very high-level viaduct here. You can see the properties, even at early ages, match those of the existing material. This was the other pioneer plants, the Simpor plant in Ivory Coast, and also here they could demonstrate how it's possible to control the color. Some people said to us, well, you know, clays are red, we don't want red cement. If you don't want red cement, you can have gray cement. But in fact, now we find that a lot of people, you know, actually quite like reddish cement because it's kind of more friendly. It's not gray and sterile, but, you know, warmer. And this is the most recent to open calcined clay plant, now the largest in the world in Ghana, and already the production is around 10,000 tons per month. So in 10 years of this project, we've gone from the early demonstration buildings to now really full-scale applications, and all of this can be done at lower cost. So we're talking all the time about green premiums, but in the case of LC3, yes, there is an initial investment cost, but in the long term, it can be cheaper. These are the plants we currently know about, but I think we're just really at the start of an exponential growth in the amount of calcined clay plants. Today we have an installed capacity of about 15 million tons, where the potential is at least 400, and the savings are around 10 million tons, where the potential is 500 million tons a year. That's more than between 1 and 2% of world emissions. So right at the end, I just want to emphasize this is one part of the solution. And what we need to do is bring the different parts together. So we've talked about SCMs. We need to also think about concrete. We need to also think about the fact that today we may be using 4 or 5 times the amount of cement we need to make a concrete with exactly the same performance. And part of the issue here is to go to more industrialized production of cement, as in ready mix, but it's certainly not to do things like 3D printing, which would drastically increase CO2 emissions. And then we can look at the next stage, how to reduce concrete in the buildings. Here the obstacles are an engineer's time often costs more than just putting in extra concrete. There's a kind of paranoia. People say, well, let's just put in another 10%, but another 10% concrete is another 10% CO2. And complexity costs carbon. This kind of rather banal building, you see none of the columns are really lining up. And in the middle there, unfortunately, the pointer doesn't work, but there's this huge, thick transfer slab, which is all extra carbon that doesn't need to be there. So we need to have tools like this one developed by my colleague in the University of Cambridge, which can evaluate many, many different solutions very early on in the design stage. And you don't need to follow all the details of this graph, but just look at the diversity. Between the best and the worst solutions, there's a factor of 2 in terms of the embodied carbon. And of course, to combine all these different strategies together, that reducing clinker in cement, reducing cement in concrete, and reducing concrete in buildings, we need metrics. Metrics at the level of the final application, like buildings, and this is where we're also working to develop simple metrics called the Global Building Data Initiative, which is one of the actions of the Globe Consensus. This is a simple way everybody can monitor their CO2 in buildings. So to conclude, I think the main message today is we have most of the solutions. Let's get on with it. Let's realize these reductions today. We have to stop this idea of, oh, let's wait till we have the perfect solution. Because by then the world's warmed, we're too late. We need to implement what we can do now, even if it's not perfect. And we need to implement on a global scale, because CO2 is a global issue. And we may have much more impact in developing regions like Africa, which are in the process of building, than we will do in developed countries like Switzerland. So with that, thank you. I hope many of you will come to our conference in Cape Town, International Conference on Calcined Clay for Sustainable Cement. We will have a big summit in April at EPFL. Everybody's welcome to these events, and if you need more information, please look on our website. And thank you very much. I won't be able to answer your questions, but we can find a way to do that.